Hello, everybody. I wanted to talk about cosets and Lagrange's theorem. So, Lagrange's theorem is a very important result in basic group theory, and cosets are the tool that we'll use to prove Lagrange's theorem. And cosets will also appear quite a bit later on in this class. They'll appear when we talk about quotient groups, for example. Okay, so what does Lagrange's theorem say? It says that if G is a finite group and H is a subgroup of G, then the size, or the order of H, divides the size, or the order of G. That's the first part of Lagrange's theorem. Let me tell you the second part, even though we don't yet have all the language to fully understand it yet. So, the second part of Lagrange's theorem says that the number of distinct left cosets of H in G is that dividend. Is that the right word? Is the quotient. The quotient, the size of G divided by the size of H. So I haven't yet defined cosets for you, but we'll see them later in this video. Let's first do some examples of the first part of Lagrange's theorem. So here we have a group, Z mod 30, the group of integers 0 up to 29, equipped with addition modulo 30. Its various subgroups are drawn below. So the subgroup generated by 2 contains all the even numbers up to 30. And the subgroup generated by 5 contains 5, 10, 15, 20, 25, and 0. I've listed the sizes of all of these subgroups. So this particular subgroup has size 6, whereas the subgroup of all the even numbers had size 15. You'll notice that both 15 and 6 divide the size of the larger group, 30. So those are examples of sizes of subgroups, 15 or 6, dividing the size of the larger group, 30 in this case. And that's true for all the subgroups of Z mod 30, right? The various subgroups of Z mod 30 are all listed below in this diagram. And all of those sizes, 15, 6, 10, 5, 3, 2, and 1, all divide 30. This drawing here furthermore shows the subgroup relations. So the subgroup generated by 10, which contains just 10 and 20 and 0, is itself a subgroup of the subgroup generated by 2, or the subgroup generated by 5. So these lattice diagrams of how all the subgroups fit together are commonly seen in group theory. Okay. So Lagrange's theorem again says that if G is a finite group and H is a subgroup, then the order of the subgroup divides the order or size of the larger group. Here are all the subgroups of Z mod 30. Their sizes are 1, 2, 3, 5, 6, 10, and 15. And all of those divide the size of Z mod 30, which is 30. As another example, here's the symmetric group on 3 elements. So all permutations of 3 numbers. Its elements are just the identity, the transposition 1, 2, the transposition 1, 3, the transposition 2, 3, and then the 2 3 cycles, 1, 2, 3, and 1, 3, 2. I'm missing a close bracket there. It has the following various subgroups. It has the alternating group A3 as a subgroup. It has this subgroup whose only elements are the identity and the transposition 1, 2, or this other subgroup whose elements are the identity and the transposition 1, 3, or this group whose elements are the identity and the transposition 2, 3. And it has the trivial subgroup consisting only of the identity. So again, let's look at the sizes of the subgroups. The subgroups have sizes 3, 2, 2, 2, and 1. And 3, 2, and 1 are all divisors of the size of the larger group, 6. Okay, so our second goal for this video today is to define the cosets of a subgroup H and G. This is a really important definition, so pay attention to it. It'll come up more as we continue. So G is our group, and H is a subgroup of G. We're going to let little a be an element of G. Little a is not necessarily in the subgroup H. Okay, so G is a larger group, H is a subgroup, and little a is an element of the larger group G. We're going to define AH, and this will be the left coset of H in G containing A. It's a mouthful, but AH is the left coset of H in G containing A. The elements of A capital H are all things of the form A little h, where little h is in our subgroup, capital H. We'll see some examples. The right coset of H and G containing A is capital HA. So now we're multiplying by A on the right. That's why it's called the right coset of H and G containing A. So the right coset has as its elements all things of the form little HA, where little h is again in our subgroup capital H. All right, that's a lot of notation. Let's do some examples. So this example at the bottom is where G is the group Z mod 12, and H is the subgroup generated by 3. So the elements in H are 3, 6, 9, and 12, which is 0, mod 12. Here, 0 plus H, that is a left coset, AH. Here, A happens to be 0, and I've written that plus because in Z mod 12, our operation is addition. Okay, so maybe you could think of like there's a secret multiplication sign between this A and the H. But in this group, it's additive. So we don't write, A multiplied by the set or the subgroup H. We write 0 plus the subgroup H. All right, so the elements of 0 plus H are all things of the form 0 added to somebody in the subgroup H. So 0 added to 0 gives me 0. 0 added to 3 gives me 3. 0 added to 6 gives me 6. And 0 added to 9 gives me 9. Let's look at this coset 1 plus H. It's all things of the form 1 added to something in H. So 0 plus 1 gives me this 1 right here. 3 plus 1 gives me this 4 right here. 6 plus 1 gives me that 7. And 9 plus 1 gives me that 10. Let's do one more example. 2 plus H is all things of the form 2 plus an element of H. So 2 plus 0 gives me that 2. Sorry. Yeah. 2 plus 3 gives me that 5. 2 plus 6 gives me that 8. And 2 plus 9 gives me that 11. One thing to note is that a coset might have multiple names. So this coset 0 plus h could also be called 3 plus h. Because when I add 3 to all the elements in h, I get the same set. 0 plus 3 gives me 3. 3 plus 3 gives me 6. 6 plus 3 gives me 9. And 9 plus 3 gives me 12, or 0. So I get the same set containing 0, 3, 6, and 9. Similarly, this coset also has the name 6 plus h, because if I add 6 to the set 0, 3, 6, and 9, I get the same set back containing 0, 3, 6, and 9. So that observation is described in the second bullet point. We might have that the cosets AH and BH are equal, even if A is not equal to B. Here's an example of that. 0 plus h is equal to 3 plus h, even though 0 is not equal to 3. Another comment that's important at this stage is that cosets are not necessarily subgroups. H is a subgroup, but its cosets need not be subgroups necessarily. 0 plus h, or the identity combined with h, will always just give you back h. So this one right here, this is just h. That is a subgroup, right? H is a subgroup. But the other cosets will not be subgroups. So this coset 1 plus h is not a subgroup. And this coset 2 plus h is not a subgroup. Indeed, the cosets that don't contain the identity, they can't be subgroups because they don't have the identity as an element. All right, so remember again the definition of cosets. G is a group, H is a subgroup. Its cosets AH or HA on the left and the right, its left and right cosets, are obtained by combining A with every element in that subgroup H. So the cosets of this subgroup generated by 3, they partition Z12 into disjoint or non-overlapping sets of equal size. So here in this top row, I've drawn G. I've drawn its elements just as dots, labeled 0 up through 11. The coset 0 plus h, we saw had the elements 0, 3, 6, and 9. The coset 1 plus h had as its elements 1, 4, 7, and 10. And the coset 2 plus h had as its elements 2, 5, 8, and 11. You'll see that G has been split up into 3 groups corresponding to these 3 cosets. And each group has the same size, namely each group has exactly 4 elements in it. The red group has 4 elements, the blue coset has 4 elements, and the green coset has 4 elements. So this is what we'll use to prove Lagrange's theorem in a couple of lectures, namely that the order of a subgroup divides the order of G. The way we'll do this is, here's our subgroup, H. We'll show that the cosets of H are disjoint, non-overlapping, and that they all have the same size. And together, if you take their union, you get all of the elements in the group. So that means that the order of G divided by the order of H, or the size of G divided by the size of H, is equal to the number of cosets of this subgroup H. And if you recall, that was in fact the second statement in Lagrange's theorem. Indeed, the number of cosets of H and G is the size of G divided by the size of H. Once again, Why is the size of G divided by the size of H equal to the number of cosets? Well, we'll show that the cosets are disjoint and they all have the same size, and together their union is the entire group. So therefore, the group is split up into pieces. Here the pieces all have size 4, and the number of pieces will be the number of cosets. Okay. Let me end our discussion of cosets for today with one last example. So our group will be the symmetric group on 3 elements, and our subgroup will be the subgroup generated by the permutation 1, 3, swapping 1 and 3. So if you do that permutation twice, you get back to the identity. And so that's why, that's why this cyclic subgroup has only these elements in it and nothing more. Okay, what is the coset, left coset identity H? Well, I just multiply all these elements in H by the identity, and I get the same subgroup back. 1, 2 H, I multiply each of these by 1, 2, and I get 1, 2 and 1, 2, 1, 3. I'm looking at the left coset by 1, 2. That's why I'm multiplying on the left. 1, 2, 1, 3, if you multiply it out, you get this 3 cycle 1, 3, 2. Indeed, 1, 2, 1, 3, it sends 1 to 3. And then it sends 3 to 1. Let me do that again. This product 1, 2, 1, 3, it sends 1 to 3. Where does it send 3? Well, it sends 3 to 1, which then goes to 2. So that's why we have 3 going to 2 in this 3 cycle 1, 3, 2. And then where does it send 2? It sends 2 back to 1. So that's why we have this closed up here. Okay, and let's look at this coset 2, 3, H. I multiply each element of H by 2, 3 on the left, and I get 2, 3 times the identity, and 2, 3 times 1, 3. If I multiply out 2, 3 by 1, 3, I get this 3 cycle 1, 2, 3. So here I have my picture of the group G. All of the 6 elements are drawn there. And you can see that my cosets, the identity H, 1, 2 times H, and 2, 3 times H, they divide this group up into pieces. All of the pieces have the same size, 2, and I have 3 different pieces, 1 for each coset. Okay. A good check for the reader is to check that this coset 1, 2, H is indeed equal to this coset 1, 3, 2, H. So try finding the coset 1, 3, 2, H and observe that it's the same as this coset 1, 2, H. Similarly, a good check for the reader is to check that this coset 2, 3, H is the same as this coset 1, 2, 3, H. You can find all the elements of 1, 2, 3, H, and they're the same as this coset 2, 3, H. I guess I skipped one. You should also check that this coset identity H, which is just H, is the same as the coset 1, 3, H. Let me end with one final remark. The coset H1, 2 is not equal to the coset 1, 2, H. So this left coset, 1, 2, H, is not the same as this right coset, H1, 2. Indeed, what are the elements of H1, 2, this right coset? Well, I take H and I multiply everything it by 1, 2 on the right. So the identity times 1, 2 on the right gives me 1, 2. And 1, 3 times 1, 2 on the right gives me 1, 3. 1, 2. What is 1, 3 times 1, 2? Well, it sends 1 to 2. So that's why I have 1 going to 2. And then it sends 2 back to 1, which then goes to 3. So that's why I have 2 going to 3. And then it sends 3 back to 1. So that's why I have this closing up. Okay? But you'll notice that this right coset H12 has different elements than this left coset 12H. You see that? They both have 1, 2. Oh, let me draw this again. I meant to highlight this guy. So this right coset H12 and this left coset 12H, they both have 1, 2 in them. But other than that, they're different. One has this 3-cycle 1, 2, 3, whereas the other has the 3-cycle 1, 3, 2. So since those are not equal, this is an example of a left coset left coset 1, 2H not equaling a right coset H12. So that's what this comment down below is saying. We don't necessarily have that the left coset AH is equal to the right coset HA, unless the group is abelian, and then order doesn't matter. All right, thanks.